This lesson is on continuity, end behavior, and limits. It's from section 1-3. So let's look at these two graphs we have here. We have two graphs. One is just a straight line, goes right through. Another one we seem to have a break in it. So we can define these functions separately. We can have continuous functions, which is what we have in A. Continuous functions. And these have no breaks, holes, or gaps. This should just say breaks. We can look at this second one. We clearly get to a point. We could call this point C. And as we approach this point C, our graph seems to change. We seem to jump from one function to another function. We're still passing the vertical line test. If we were to take a line and go through, we don't have more than one y value for any x value. You can assume this is x, this is y. So we're still a function. We just have a discontinuous area. So continuous functions approach the same value from left and right. So again, looking at that second graph, we can call him B. We have some, where as we approach this value C, we have some value expected right here. But as we approach from the other side, if we were to approach from right to left, we would expect to get this value C up here. So what we're saying, in order to have a continuous function, you have to approach the same value from left and right. We talk about this with regards to limits. What's written here says lim f parentheses x, close parentheses equals L, and then we have x, arrow, some C. The way we read this is the limit of f of x as x approaches C is equal to L. It's just the way we're going to read this. This is going to come in handy for the rest of this chapter and for pre-calculus. So we have three conditions in order to satisfy continuity. The first one is that f of C exists. So we have to have some value. If we plugged in C, we need to make sure we're getting some value. We could have C in this graph too. We plug in C to our f of x, we get some value. The second one is that the limit of f of x exists as x approaches C. So we need to make sure that we have a limit, we're approaching some limit as we're approaching that value from left and right. So as we approached from the left over here, we had some values. We approached from the right over there, we had some different value. The third one is that limit of f of x equals C as x approaches C. So we need to have our limit equal to that value C as we approach C. So we can talk about this function as discontinuous, and this function as continuous. So discontinuous functions are functions that are, surprisingly, not continuous. That's how we define them. So if they do not satisfy these three things, then we call them not continuous. So there's three different types of discontinuity that we have. First, we have infinite discontinuity. That means the function increases or decreases indefinitely as x approaches some C. So if we had a graph that looked like this, and it looked like this over here, and this was the value C, wow, those are really good lines, then we would call that infinite discontinuity. As we approach this C, we're going higher, 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 and lower, lower, lower. We're never really getting to some value. We can also have jump discontinuity. So that looks more like this, which is, if you remember, what this first one looked like. So jump discontinuity is defined as the limit from left and right exist, but they have two distinct values. So if we were to approach as we go from left to right, or from right to left, up here we get this value as our limit, down here we get this value. So if they're not equal, then we say that that's a jump discontinuity. They both exist, but they're not equal. We also have removable discontinuity. That graph looks something like this. We'll put that up here, and we'll call this C. So it's continuous everywhere except at some value C. So if we were to change this and just pop this little value back into the rest of that f of x, we would have a continuous function. It's only discontinuous at that location. So let's look at some examples. Determine whether f of x equals 2x squared minus 3x minus 1 is continuous at x equals 2. So we have to look at our conditions. The first one, does f of 2 exist? We will say, yes, f of 2 exists. We can plug in 2 into this equation and come up with some value, right? We get the function defined at x equals 2 is f of, f of 2 is equal to 1, if you worked that out. Does the limit of f of x exist as x approaches c? So now we can write a table in order to define this. We plug in 1.999, 1.99, we plug in 2.001, 2.01. What we're doing by doing this is approaching our value from the left and from the right. And we're seeing what's happening as we get closer and closer to that value of c, which in this case is 2, as we approach from left to right. So when we work these out, we get 0.95, 0.995, and then when we have 2.001, we have 1.005 and 1.05. So if you were to look at this table and try to guess the pattern, try to see what's going to happen, you could probably guess that the value we're approaching from the left is 1. That's the value we're approaching from the left. And the value we're approaching from the right is 1. So we would estimate that the limit of f of x as x approaches 2 is equal to 1. Does the limit of f of x equal f of c equal f of 2? Are these equal? Yes, we say yes, and we can graph to check our solution if we wanted. We won't do that right now. So we would say yes, this function is continuous. Next, we can look at end behavior. This is another thing that we need to understand about our functions and how they behave. It describes how a function behaves at either end of the graph. So this means the left end behavior, we're looking at f of x, the limit of f of x as x approaches negative infinity. So if we plugged in the most small values, the most negative values we could, we are going to get some value. Our graph is going to do something over there at the negative infinity end of our spectrum. And if we looked at the right end behavior, limit of f of x as x approaches positive infinity, as we plug in positive infinity for these values, our graph is going to do something. Our f of x is going to have some behavior that we can define. So another example, use the graph of x over x squared minus 2x plus 8 to describe its end behavior. Support graphically and numerically. So what does that mean? Support graphically and numerically. Graphically means look at this graph, tell me what you think is going to happen. So if we're looking at x as it approaches a negative infinity, we're looking here and it looks like it's important to notice we have just 0.1, 0.2. We have a very small scale already on our y-axis. And as we move left, we're already at negative 30 on our x-axis. We're at like 0.01, and it seems like it's decreasing, negative 0.01, excuse me. And then as we move farther and farther to the right, again, it looks like it's just decreasing and decreasing and decreasing. If we pulled this out to infinity, we would probably hit that x-axis. So I'm going to guess, as looking at the graph, that the limit of f of x as x approaches negative infinity, it looks like it's also going to hit that x-axis, is probably 0. And the limit of f of x as x approaches positive infinity is also probably 0. We can support this numerically by making a table, plugging in values. You look at the left end, so as x approaches negative infinity, you type in some negative numbers, bigger and bigger and bigger. If we type this in, negative 100, I think we get negative 0.01. Negative 1,000, we get negative 0.001. Negative 10,000, you get negative 0.0001. So you can see we're getting smaller and smaller and smaller, closer and closer to 0. The right end, same thing happens, except we have positive numbers. but we are getting closer and closer to 0. So we would say, to describe its end behavior, the limit approaches 0 from both the left and the right. So this would be your answer.